Hello, everyone. Welcome to another meeting of our conversational AI reading group. Today we have two great speakers, Andros, Tjandra, and Bowen Shi, talking about Sam Audio, a very famous paper that many of you probably heard about that. As always, if you have any questions during the talk, please share them in the chat or raise your hand to ask them yourself. Without any further delay, the stage is all yours.
Hi everyone. Good afternoon from New York. So today we will present our works. It's called the SAM Audio, segment anything in audio, which is like a foundation model for like general audio separation. So today, Bowen and me, we will like try to represent our group to present about this work. So this is the outline from our presentation. So we will start with the background and motivation of these works, and then after that we will talk about the same audio model, and then after that we will talk about how we curate our training data, and after that Bowen will talk about the evaluation data and tasks, and then Sam Audio Judge, which is like the judge model that we create and then we share to the public as well for the automatic evaluation for the separation task. So we will talk about like the result of those evaluation, and then lastly, we also like have like some ablation studies explained in this presentation, and then we will talk about the conclusion in the end. Let's start with the background of this work first. We in this work we mostly focus on the audio source separation task. So the aim of this task is basically try to decompose a complex sound mixture into like the individual sound, so the source tracks correspond to the distinct sound events. So basically you assume that the complex sound mixture is basically have sound A, B, and C, and then your goal is you want to extract one of the distinct sound event, let's say sound A, out of these three sound mixture. So in general, I think for this kind of works, mostly you can like try to generalize a lot of prior works into like three different branches, which is like first is like you have the speech separation. Is try to I think mostly people focus on like isolate the human speech from the background noise or like multiple non-related speech sound event from the background, or like even like the you have like another task that try to separate multiple speaker and you only want to get one of the speaker. So there are like some prior works that are pretty famous, for example, like the ComTaskNet and then the Stepformer. Second thing is like the music source separation. Usually we try to decompose like a music mixture into like fixed ontology of time. So basically you give it a song and then you will try to separate into like vocal, drums, bass, and other. And then prior works that most people know is like demarcs and splitters. And then last is like the sound event separation. Basically, you give like a mixture of sound events, basically, and then you try to extract the general sound events out of those using like most likely people use the text description. But I think this kind of model usually struggles on like complex music or like speech separation because they are not specifically trained for that task. So I think prior works is they are famous for this is like the audio step and the clap step. So there are like some limitation of the existing model. I think first one is like they are mostly like the domain specific architectures. So the model is specifically like tuned for either like speech, music, specific sound effects, and it's not really generalized well across the domains. And then second thing is like they are usually support only like the fixed closed set categories. For example, for music, it has like there's some predefined taxonomy like the vocal, drum, and bass. I think like for example, Tmax they support 4 to 6 type of uh, input only. And then they cannot do like any uh, more. They cannot do like open domain mixtures well because they only train with song, for example. And then for like the some general audio separation, they usually train with like I think like the audio set taxonomy, so you can only prompt with those kind of vocabulary from the audio set itself. And the other thing is like they only do like the second so like single prompt modality, so means like they only support mostly people just support the text description as the prompt, or like even like for like uh music separation they only support They don't even support prompts, so they just directly output like six stems directly from the model. It's like already predefined by the model, so it cannot do like any complex scenario where you want to like prompt with like some combination. Other thing is like I think most of prior works they don't really have like the unified evaluation. I think most of the evaluation that they have is mostly like from the simulated environment. For example, like I think for the speech separation, they do like the Libri mix data set for like the evaluation. But I think in this work, we will try to build like a benchmark that come from the real world data set. Okay. So basically, in general, we try to build a unified foundation model to cross the limitation of these existing works. So we try to handle arbitrary sounds across all domains with the flexible and multimodal prompting. So the inspiration for this work is actually like come from the SAM that are uh, famous in the computer vision world. So in the SAM, in the for the vision itself, they try to replace segmentation model into like one single foundation model. They allow flexible prompting. They allow like people can click on the image or like draw the bounding box and also or type the what is the item they want to segment out and create the segmentation mask. And then last thing is like the have like zero shot generalization so they can do like segment from an unfamiliar object without additional training. And then we translate it to our model as our goal. So we want to build a unified task, try to gather every domain into like one foundation model, do the like the flexible prompting. So not only the text, but you can also have the text and then visual mask or like even temporal spans. And then after that, we will do the open domain generation, means like that we try to make our model robust to like the arbitrary mixture of the sounds that try to simulate like the complex or reward mixture or like in general like the sound in the wild basically. So yeah, it's similar to the previous slide. Basically, we try to aim to create a model that can do like open domain, extract arbitrary sound beyond like the fixed taxonomy and predefined categories. And then we also will do the multimodal prompting, text description, visual mask, and temporal spans. And after that, one of the thing that we try to will here is like the generative separation. So compared to like the more traditional discriminative model that usually you predict the mass of uh, the mixture that you want to extract, we directly generate out the output using the flow matching. So it basically it try to make our model to produce like more natural and high fidelity output compared to the masking approach. They usually have like some artifacts due to the masking itself. So this is our model. This like the like everything that our model can do. So we have like several brands of the input and output. I will talk about them one by one in the next later slides. So in general, let's talk about the prompting more detail. First, we have like the text prompt. Like usually people can type what they want. So you give the audio mixtures and then you uh, can type right what things that you want to extract out of this. Usually we prefer the input to be like similar to the same, where they have like the noun phrase and then the verb phrase. Basically, like for example, in this example, we have the dog barking and piano playing, or like people speaking. For example, if you want to extract out the speech, and then we use the clap text encoder and sorry, we use the T5 encoder, and then we have the visual prompt itself. We basically, I think in this use case, we can put like video with audio, and then the people can click on the video, select the object they want to extract out. For example, you have like the dog in the video, and then in the background there are like some, let's say like some car driving noise or like traffic noise, and you click the dog, and then you only want to segment out the sound that come out from this object, basically. And then for that we use the same tool plus the visual encoder. So basically same tool is to generate the mask, and then you mask out the things, and then you should get the features using the visual encoder, put it like project it to the our same audio model. The last thing that we introduce in this work is like the span prompt thing. Basically it can like give like the audio, and then you can like people can create a span of what object they want to mask out, which is I think this is useful. For example, like you have two when you have like two very similar sounds, for example, like two people speaking, and then you want to extract only one of them, for example, you can just select the region where this happens, where the first speaker or second speaker, depends on your target happens, and then you can like extract out of this. Because if you type with the text prompt, then you just type speech and you extract both of them. But if you combine with the span, basically you can say speech and then you extract one of the speech that are isolating. So basically in this span, you can only like get the speech that you want to target. So visual prompt head, basically you have the video, you use same tool, generate the mask, and then apply the visual encoder. So for the mask generation, we use the same tool, and then we have the perception encoder to extract the features from the frame level features. And then after that, we do like some projection and then add that to our diffusion transformer as the input, as the conditioning. For the spam prompt head, basically in the UI, you can assume in the UI, basically you can like select what region you want to select. You can do more than one. Basically, it's like basically you just need to provide the start and end times for the target for the sound, and then like you can like precisely control in the frame level to basically just to inform the model what sound you want uh, in this region basically. And you can also combine with the text itself to make it more detailed, like the example I provided before for the speech. And then after that, it will be converted into like token. Basically, it become like the we have like embedding, which is like plus and null. Basically, plus means like the sound is active here. So basically, this span is like converted into like the kind of like phoneme, basically in the like timeline phoneme into like the audio itself. And then lastly, you have like dedicated span encoder, like basically try to make like this as an input conditioning available for the diffusion transformer itself. And then the last thing is like the text prompt. So basically, you have like the natural language, like I mentioned before. You mostly prefer like the noun phrase plus verb phrase, like the dog barking, for example. And then we use the T5 as a our text encoder. It's like we basically we don't fine tune the T5, we just use as it. And maybe it will like capture like the semantic from the input itself, and then try to give it to the diffusion transformer. We use the cross attention for the conditioning in this case. So for the audio encoder and then the latent space representation, here we use the DEC VAE latent space. So I think DEC usually is like the some kind like the encodec improvement from the encodec, but here because we do the flow matching, we only care about like the continuous space, so we don't use the quantizer here. We use the DEC VAE directly from the continuous latent space. Uh, and then here we have like the repository as well for the deck VAE itself. So I think if people interested to use, they can use this for their own project as well. So basically, I think this work is we try to use like some improvement from the deck. We try to reduce the dimension to make it the sequence shorter, so it make our model more efficient. Also, we train this model with the 48 kilohertz, so it can do like the high fidelity for the acoustics details. It preserves like the high frequency during the high quality audio construction. And then for the audio encoder, we take the representation from the complex audio mixture as the input, and then for the output as well, we also like the encode them into like the latent space. So we do the input and output prediction in the latent space. And then for the conditioning, we just provide the necessary context for the diffusion transformer on the targeted separation. So in the last part is like basically the diffusion transformer and decoder. So first part is like we use the flow matching. We try to match learn the mapping from the simple noise distribution to the complex data distribution on the target audio. And then in this work, instead of like only predict, so I think most of the work they when they do the separation, they only predict the target audio. But in this work, we actually try to predict both of them, both the target and then the residual. So we will explain the motivation later on. But basically, in general, it's like you want, let's say you have like a mixture of A, B, and C, and then you want to extract out two items. Then what you can do is like you can like prompt with the object A, and then the residual will contain B and C. And after that, let's say you want to extract B. So instead of extracting B again from the A, B, C, you can extract the B from the B and C. So it make your task become easier because you only have like less object. And then let's say you want to, let's say it contains error, it is easier to, to pick out the error from the B and C instead of like the original complex mixture A, B, C. So this is one of motivation. So basically you can do a chain of extraction from like very complex sound into like reduced by from n to n minus one, n minus two, and until like you only have like one. So you can do like the process by elimination as well. If you find there is some sound that you cannot easily prompt or like, you cannot easily describe what is it. So this is the motivation for the target and residual audio uh, output jointly. And then last thing is like we use the DECV decoder to generate the from the latent space into like the high fidelity audio waveforms. Okay, so yeah, okay, actually I already talked about this, so I can skip it. So the diffusion transformer, but in the core is like basically we have like our model use like the flow matching architectures based on the DIT, the diffusion transformer framework. And then we also do the joint generation. I explained it before. And then for the scalability, we also train three different models, like 500 million, 1 billion, and 3 billion. We will talk about this later on. So in general, okay, let's summarize the thing. So the input is basically you have the Gaussian noise, and then the output is like basically a join of like the target and residual audio. Input conditioning is basically you have like the input mixture, the audio mixture, and then you have the conditioning text, video, and the span. So if people don't provide the text or video or span, it will become like basically a null, like just like blank embedding. You can like assume it's a dropout. So during training, we also apply dropout on this to cover all this, like some case where some of the modality is missing. So in general, we train with like normal, like the flow matching objective. But in this case, we also like add some the auxiliary alignment loss. Basically, the idea is like you take the hidden representation from the diffusion transformer in the middle, and you put like some auxiliary uh, like multi-layer perceptron heads, and then predict there's a vector. So the vector that we want to align is basically you have the output target, you extract the AED, the AED embeddings. So in this case, we use the PAN as our model to extract the AED embeddings, and then you try to like um, um, maximize the cosine similarity between them. The idea here is like you want your hidden representation to be aligned with whatever the sound events that happens in the target. And then this is like the soft target, so you can basically train with this kind of like the cosine similarity loss. So in the final loss, basically you try to add between the flow matching and then the auxiliary loss with like some coefficient to like to put the weight on the how much auxiliary loss you want in the final loss. So we have like three different model here. We have the same audio small, 500 million parameters, and then same audio base, 1 billion, and then same audio large, 3 billion. So basically, we train with all of these model. We train with like two-stage recipe. We have the large-scale pre-training on the synthetic mixtures, and then followed by fine-tuning on the curated high-quality data. So in general, 500 millions is like A small model is recommended if you have maybe like lower resource hardware, or like you want to like run pretty quick prototype iteration or something like that. And then like the our base model is the 3B. So it usually in our ablation study we show that it demonstrate like the best performance and then use for all of these key comparison. Okay, so now the for the next part is like I will talk about the training data overview. So here is like how we categorize our training data. We have like first is like the fully real triplets, which mean you have uh like all three things together. I will explain later on. And then we have the synthetic mixture, and then last we have like the pseudo label stems. I will explain this one by one from now. So in the mixing strategy, first one is like fully real triplets. The use case is, for example, I think in some data set like the MuseDB, you have like the multiple audio stems basically. So you can actually you have like the input mixture from them, and then you have the target basically pick one of those stems, and then the rest of them is like the residual. So you just like combine the rest of them, like single out the target. So in this case where you have the fully real triplet, you can either use the mixture directly, or in our case that we also like try to remix them, but not by changing the SNR too much, because those triplets is probably like already like pretty close to the real human data, basically. And then in the second type of data is like the synthetic audio mixtures, which is like you don't have the mixture itself, and then you have basically you just pick one of the audio as the target, and then you randomly sample from data set or like from even like other domain. For example, you first the target is like from the some like guitar song from the music stem, and then you want to sample uh, the residual from like the audio set. For example, you just sample like random noise, or like sample like the animal the sound basically from the data set. So you just create them. You just like create using like the mixture. So in this case, you create the mixture using the SNR around like plus minus 50, and then you can create the mixture, and then you have the rest of those noise become like you combine them become the residual basically. And then third one is like we have also do like some pseudo labeling pipeline. Basically here that you have the audio mixture, and then you give it to like a PLM, which is like the perception LM audio encoder. You try to predict what instance, what sound event happen in this audio mixture. So let's say in this audio mixture you have like the you have the thunder, raining, and music, and then you will give this prompt into the same audio model that you already trained before. So basically, we do like several iteration. Every time you get like better same audio model, basically you try to generate this again, the pseudo label output. So you give it to the existing model. Now you get the target and residual, and then we apply several filters to filter out what is the good example to be included into our next round of training. So here is our data filtering criteria. First, we try to make the quality assurance. So basically, you only want to include the high quality training. So every all like pseudo label samples, we do like very strict filtering, which is okay because you have like ton of data, and then you can do like multiple rounds after that. So in the end, you have like a set of high quality data that probably like very close to the real fully triplet mixtures basically. And then after that, you will do like the text audio alignment, you do the clap uh, score threshold, try to only pick the sample that are closely aligned with the text prompt, basically like high clap score. Audio quality, you want to make, so here we use the audio aesthetics, we try to predict the production complexity, which means like the audio should have like pretty low complexity, means like you single out one of the stem out of the other, try to guarantee the perceptual quality of the extracted sound. And last is like you have the VAD applied to the specifically for the speech examples. So basically, you want to ensure that there is like some something happens in the uh, in the pseudo label. So it's not like all silence, which is not useful. So you only like want to some example that are not totally silence. And then I think for the video pseudo labeling, you also care about like how many, sorry, go back. So you only care about like how many masks you generate. So you don't want the sample where you have like very few mask coverage, and then you also want to have like the image bind score between the target audio and then the image that you mask to be pretty high. So it means like you have like high correlation on what kind of audio the target you mask can generate. So this is like the visual pseudo labeling pipeline. You have the audio mixture as the input. You run the same audio pseudo labeling. You have the get the target residual audio and then the text prompt. And then now you run the same tree. You have the raw video and you get the mass audio. This is how you get the mass version uh, of the training data out of from the raw video itself. The last thing is like the span data construction. So basically the span data construction, we focus mostly try to get like the high quality data, and then we focus on like more like sound effects like spiky and discrete sound, like for example dog barking or door slamming, rather than those continuous ambience like for example like continuous song or continuous speech itself. Uh, how we get this kind of temporal span is like we apply the VAD, basically try to get like the clean target audio with the threshold of 40 minus 40 dBFS, and then we at least like 250 milliseconds on this region of the active sound. And then after that we just try to mix with like some residual audio itself, which is like the you just randomly sampling like some unrelated noise category. Is like different from the target audio, and then most likely you try to sample the audio that are span pretty long, so you can like pick out the small span out of this like background noise or something like that. So in this case, here is the example. You have the target audio is like pretty discrete and choppy, and you add like some residual audio continuous, and then you add them. Is how you get the mixture for the span data. And then for the prompt generation, text prompt, we usually use the PLM and then some LLM to generate like the caption audio mixture. And then usually if you have like long caption, we prefer like shorter caption. In that case, then we usually run LLM to do like some post processing to make it into like shorter version, like what item you want to describe in the non-phrase and for phrase. And then for like some category, we also use like some pre-trained classifiers. For example, like you have like the speech and you want to say like I want to extract female speaking, but some of our data set doesn't have that, so we run like some gender classifier to predict those categories. And then for the visual prompts, we use the same tree to extract the mask for the target sound based on the target sound caption, and then image bind to filter out those unmatched, like purely matched pairs. And then we also use like the full video clip without explicit masking during the training and then during the fine tuning as well. And then lastly, it's like the span. Basically, I explained before, you have like the temporal window sampled from the good, from the like the high quality sound effects data sets, and then you have it allow like the model to have like some grounding on the what sound event you want based on like user inputs, and it is pretty flexible. Basically, all these three modalities you can like combine each other. You can like prompt together or like prompt separately. So it basically, if you prompt together, it sometimes it also like enhance your output. Uh, okay, I think this is from my side.
Yeah.
Any yeah, okay. Maybe Bowen can continue first, and we'll do Q&A later.
All right, yeah. So I'm gonna like continue my presenting. So like first thing is in the like one major kind of major point of this paper is also the evaluation side. So the existing benchmarks for audio separation, we notice that mostly are like some synthetic audios. Like basically people like just mix the two audios, and then like you have a say you have a text query and you want to like get the extracted sound out, and so that like you have the ground truth and you can measure the or like signal processing based metrics. But we find like it's not really that optimal because in reality, like you always want to apply the model to like real audio where you have a different audio stance mixed in. So like in this work, we propose the same audio bench. So same audio bench is like we take all the real world videos and also like just based on same audio, we provide the three different prompting modalities like text, visual, and span. So all these real videos are paired with this like through human annotation. And like all the videos are real and they are also like human annotated. So in terms of these tasks, since like same audio, the kind of one highlight is like we try to is generalize that to all the different separation tasks. So like during the construction of the same audio bench, we also like cover all the different domains together. That includes speech, music, and music extraction, as well as like the instrument extraction from the music. And on the speech side, you have like you want to extract not just a speech, sometimes you want to isolate certain speakers, so you can do like a speaker extraction. And like you also have these in the wild cases where like say if you're in a street like recording, you want to extract the guitar, so you do the instrument separation, but like on the noisy mixtures. Of course, also in covers these like general sound events like something like dog barking or raining. So this is a rough like coverage or like statistics of these same audio bench. So on the left side, you see this we see a different number of like test items and in the each modality. Um, the most like instrument is has the most, and also you have these like like for the speech. Sometimes like you have like most of coverage on the three modalities. This is because like in the speaker separation case, where like sometimes like it's very hard to say describe a speaker and like separate. Gender is probably the one thing that you typically use as a man speaking or like female speaking, but in other cases you have to rely on other modalities like span or visual. So that's why like during the in the same audio bench, we also mask these two additional signals, like where these people speaks onset and offset, and like on the visual side, you get this like person's like speaking video. So on the right side are the source of the data sent audio bench is from. So we mostly source it from these public data sets, like AV speech. This mostly for speech, and there are like different people speaking together in the conversation, so you can like get the speaker separation. Also, sometimes there is noise. So the others are like condensed movies. Condensed movies mostly for sourcing this professional videos. And also like music ABQA is mostly for sourcing the instrument separation under more in the wild environment. And also like the audio set and music, the music data set is like you have the different videos paired with like people playing instruments. So you can get like an instrument and like get the visual mask paired all together. And also like the VG sound. So roughly speaking, like the for like the instrument, for example, it's mostly from these like two music data sets, and for the like music, it's coming from say like the audio set and the condensed movies. So the like detailed annotation process, you can find it in the paper, but like very roughly here, just a like very high level introduction of the annotation process. So we have these like three annotations. At first, text. So annotators like given this like audio mixture, and they need to write down pick the target sound and then write down the freeform descriptions, and to match it with like with a training or like in general like find the force separation, it might be easier to describe a sound with some like MPVP phrases instead of like free form sentences. So that's like where also annotators are notified to write these captions instead of like just the full sentence. On the visual side, the annotators are required to annotate the visual mask. So they will draw the bounding box, and based on the bounding box, we use send to engine to like convert that to the visual masks at at full frame rate. So you have this like a masculine, which is like spanning across the whole video corresponding to the sound if the sound is on screen. And also we have the span annotation. So the annotators, like given the target sound and the audio mixture, they need to mark the exact start time and end time of this target event. And then like span annotation or like in general span as I'll present later, so it's very effective for this spiking sound extraction and like when especially like when it's very challenging when you mix the target sound with some like high volume noise in the background. So yeah, so in like when during annotation, we notice a few kind of a very challenge cases. First is like sound is usually like quite overlapping and the target sound it can be very low volume. So you have like a very heavy background sound, which makes like the annotation quite tricky. Or like the similar timbre, especially for speech. You have like two female speakers speaking together. So it's a bit hard like to say associate that either with the time span or the visual. And like the low SNR ratio, this is similar to say overlapping sound or like background noise, where target sound is generally quite low volume. So we do kind of a heavy filtering for the test set items to make sure like it has a broader coverage of these different conditions. So the next contribution of this paper is also related to evaluation. So we propose a model called Send Audio Judge, or I short for like SAJ. So this is like kind of the first automatic metric for audio separation. As I mentioned earlier, like most separation work early, they do this synthetic data. So you have the ground truth and then you can use signal processing based metrics. Or like more recently, people use like FAD, KL divergence, IS score, like inception score to measure like some statistics on the feature space. But these are one issue of that is like these metrics are not specialized for the separation. So here we propose a model and also like metric called like a SAJ score. So what SAJ score does is you take the input mixture and the target audio as well as the prompt you give. Like here we mostly focus on text prompt, and then it will give you the score of this like separation. And this score is like broken down into different parts, like recall, precision, faithfulness, and overall. Also, like the model training involves some additional signal, which I will talk about in the next two slides. So the SAJ, like so first is this SAJ model is trained with the real data. Like so humans give the score to ratings. So when we ask human to give the ratings, we ask them to give rating on the four dimensions. First is the recall. So when you extract the sound from the audio mixture, the first things you care about is like where the target sound is like fully captured in the output. So recall measures that. So if you want to extract dog barking or dog barking within the target, then you get like perfect recall. And if like some barking sound is missing, then your recall is a bit lower than like perfect. The second one is like a precision, and that's also quite important for separation because you want to remove the noise. So like as long as you get like you have a lot of noise in the target sound, then you did a like poor job on the precision side. And if you like clearly remove everything, then you get like a perfect precision. The next one is like called a faithfulness. So faithfulness measures like how similar the target sound to the original mixture. So in many separation systems, you hear these like artifacts quite often. Like it's a common failure pattern. So good faithfulness measures like whether the sound itself is like distorted or not from like in the top extract audio like from the original one. And like combining all these like three recall, precision, and faithfulness, you also give an overall like overall quality for the target audio. So that's the four dimensions, and the SAJ is also like used to predict these four dimensions, and it gives like when the user use that, you get like four scores. But typically, like if you are lazy, then you can just take the overall quality score. So this is another like kind of auxiliary task we ask humans to do during the annotation stage. That's called like a difficulty dimension. So it's more related not to the directly the quality of extracted sound, but more on the how difficult like the nature of the task, how difficult this task is. Um, because like we realize in reality, many audio separation is not really all equally difficult. Some sound they are relatively easier to extract but some are like relatively harder. So we quantify these time like difficulty into different five like different dimensions. First is like just counting and show how many like non-target sounds are present in the audio. If you have like audio mixture is very complex and a lot of like noises, different type of noise, then it's naturally hard. And second is like overlapping. So if say like your target sound is always like 100% overlapped with a non-target sound, always like the two sounds are always complement each other, then this is also considered quite difficult. And third one is like volume, so more like loudness. The target sound, if it sounds like very loud and non-target sounds is a low volume, then it's relatively easier. And last one is like confusion. So the non-target sound sometimes it can be like pretty similar to the target sounds. For example, like when you extract the instrument, maybe like a guitar, electric guitar, and like a classical guitar, they are pretty like similar in terms of the sound like timbre. So this is also considered like a hard case. So like given all these, and also people give a like overall rating on how difficult this task is. So this is a kind of a proxy task. It's not directly like a for say measuring how the system performs in the sound separation, but people can use that to construct like do the data filtering or construct the sound data sets, which is like quite hard, and you use that to like boost the model training by using the difficulty dimension. So that's the data, and this is an overview of the SAG model. So the SAG model, we take like the input is you have the input mixture and output audio, and here we also on the prompt side we mostly focus on the text prompt, but we have a separate paper on the SAG, and there we extend that to the general prompts like visual prompt and span prompt. So the model does like some similar, it's like kind of similar to the same audio. So we also do the user transformer and do the self-attention on the input and output audio. Like they are concatenated together along the channel dimension, and then we run self-attention. And text prompt is not like aligned, so we run cross-attention on the text prompt. One like so when like kind of a thing we find it very helpful to improve the SAG model is we do an auxiliary task instead of like just directly predicting these four-dimensional judge scores. That is like you predict whether the target sound is absent or like present. So we do this like via two-stage training phase. First stage is like you just use synthetic data, like you have the input mixture, which is like mixed with like two audios, you randomly mix them, so it's synthetic. And you have the text prompt as long you have a text prompt because you know the ground truth, and then you can like predict whether this target sound is like absent or not, and you randomly like flip that. Say if you want to extract the dog barking, so you mix that dog barking with say like a raining, and text prompt is dog. So one case is like you extract the dog and target sound is dog barking, so it's like it's like present, and if the target sound is like a raining, then it will be absent. So it helps the model to like kind of learn better, like understand better what is a target sound, cause like a if without this objective, when common failure mode we notice is the model is sometimes like it just focus on the cleanness of the target sound, but it doesn't really care like oh what's inside, like, whether you extract the target sound correctly or not. So this is like a very helpful to mitigate this case. So through this like training stage and the last and next like fine tuning stage, we leverage all the human annotation data to predict these four dimensions. So this is a comparison of SAJ to the previous models. Like, previous models, there were people use like a CLAP score as a proxy. And also like more recently, I use LLM as a judge. So you can get like Gemini score. Like basically you have the two audios and feed to Gemini and have some text prompt. And then you measure along these like four dimensions because like you can feed text task description of the 4 dimensions into Gemini as well, and then you get a score. So like SAG like gets like a much higher score than all the baselines here. And like here, like we measure the correlation, Spearman and also Pearson correlation. So now present the like main results for the scenario model. So here's a quantitative metric. So we compare to a bunch of baselines in the literature. Like AutoSep, FlowSep, like Splitter, DMux, these are like many of them are models, public models, open source, so you can directly compare to. And some of them are specialized, like DMux, you can only do like 3 or 4 instruments, and so we can only measure that on the instrument pro test case. Some of them like AutoSep, FlowSep is more general. Though these two work like mostly focus on general SFX, but in principle you can prompt anything like just instrument, but like it doesn't really perform well on the instrument case. The other like set of the test models, like baseline models, we compare to are the proprietary models. So many like startups, they make these like separation models, and they are very high performing and used quite often for like content creation or for like people doing the data cleaning for like large scale model training. So these include say AudioShake, Phaedra, like Lala AI, Auphonic, and 11 Labs. So some of them, like mostly, they are on kind of 2 domains. One is on speech, and then the other one on instrument. But these are very high performing, as we noticed. So we compare to like all of them, and a bunch of them, especially on the public side, they are more general, so you can prompt that. Majority of them, they are focused on one domain. So we compare to all of them, and as you can see, like on the different metrics we measure, SAG score, clap, SAG is what I mentioned, like judge score. So clap is like say text, so you have the text and target audio similarity. And overall, this is a subjective score. So we ask like during the subjective evaluation, we ask a human to give like overall, how do you think this extraction is? So the overall score, like compared to different baselines, we like outperform them by quite a large margin. And as you can also see, like just from the absolute scale, these are general sound effects extraction is relatively like harder. So the score is like lower, like much lower than these other cases like speech like denoising or like a speaker extraction. So in the subjective evaluation, we do a pairwise comparison as well as like have a absolute rating. That's where like previous subjective score come from. So in this like pairwise, you can get the net win rate, which is like a win minus lose. So if you have like positive, that basically means like your model overall like wins over the baseline. So similar to the trend we see in the previous table. So the scenario model outperform all the baselines. Compared to these like public models, it has like much larger like a margin. And specialized models like Lala AI or like AudioShake, they are very strong like speech denoising baselines. And also like for some instruments, there are many professional tools used by the musicians to get these instruments. So they are like very good at this domain. So the margin is relatively small, but like still we essentially outperform that by quite a bit. So this is a text prompted. So next, this one show the visual prompted. So visual prompted is relatively new and much fewer baselines compared to text prompted. And the task itself is very hard. And like prior work, they mostly focus on the specialized domains like a speaker. So here like IINet and AV Mode Format 2, they are like doing the visual prompted speaker separation. So you have a like in a conversation scene like people speaking talking to each other and both speaking occur in a certain time frame. So you like if you like get certain people's like face and you want to extract that particular person's speech, so that's a task. So we compare that to this like which we call like speaker separation, visual prompted speaker separation. This is one test set. And we also compare it to the other models on the more general case, like clip step. This is one model. So they do a like weekly supervisor setting where you want to say feed an image or feed a video, and this whatever object this video takes, and you want to get that sound. Since here we focus on we have the mask, so we always like feed the mask video to the model and get the target sound. Also, like a more recently, Davis flow use flow matching and training the visual grounded separation. So they can, in principle, do the general things. Although they also offered a like specialized model, fine-tuned on the music data set. But in principle, they can do all the three. So we compare to all of them, and also like their specialized model. So on the visual side, Zen Audio, that model I also outperform all of them. Though actually, this model is the same model as I presented in the previous slide. So it can do all the prompts. But like these models are just for visual. So similarly, like on the net win rate, you are like we win all of them. Maybe in David's flow, you have more on par. So given this confidence interval, so if you look at the overall score, actually it's like much worse compared to text prompted. So this is like a visual is generally we find it pretty like vague and hard. For things like a speaker, you get like strong visual clues for the target sound, but when sometimes like we want to sound like extract some very fine grained sounds like a person like closing a door, this like a slamming sound. It's very hard to specify what sound is through the visual. So that's why like in the general sound effect side, it's pretty low scoring on the visual side. So this is on the span. So span is something like this work we propose. So we mostly compare to ourselves. So we compare span to the text. So these two are like auxiliary. So you can also do the text plus span, like compare that to the text. So these are the results, net win rate, and we compare that on these five different subsets of the Zen Audio bench. The the more dark blue are the span only versus text only. So in the cases of like general sound effects speaker, you get like a pretty strong performance by just using span. But for the speech, music, and instrument is worse performing compared to the text. This is mostly because like in these three cases, the target sound and the non-target sound usually they are have very high overlap. So spam give you like the timestamp only didn't give you much like information on what you want to extract. So the model usually fails. But if you have the text plus spam, you really get the game on every case for all the different domains. So now kind of these two prompting modalities are complementary to each other. They can help when like one modality fails. So like given this result, we can also do the like spam prediction. So we leverage a model also from our group as I call it PA frame. So what that model does is it predicts spam automatically given the text prompt. So like in the previous slide, the spam are like human annotated because we have a test set, so the test set is through the human annotation. But in reality, you don't have to rely on that. You have a text, say dog barking. You can use a model telling you where this dog barking happens, and you use that as a pseudo span and feed that to the model, feed both the text and the predicted span. So if you feed both, actually we see the model gets pretty significant boost on almost all the cases. Instrument like Pro is maybe you still lose a little bit, but it's still quite on par. But on all the other cases, it's getting like it's very effective, and you get like a much larger boost by using the predicted span. So like the general sound effects is one very typical example where like you get a huge boost, and we find this like spans especially helpful when you did extract this spiking sound like dog barking. It only occurs at these like short time intervals, and you can predict these spans quite well through the PA frame. So once you feed these timestamps to the model like figure out what you want to extract like much better than just through the text description. So our like same audio model, you can also remove the sound because it predicts the residual and the target sound. So like previous slides, we mostly focused on the extraction. Now this is a removal result. So we compare to the two also like proprietary models, AudioShake and Moses AI. So like these models, it can remove the music. Say in the video you find online, and there are some like usually some background music. So there are some needs that you want to remove the background music. So this is like these two models where it does. And like same audio compared to them, we also like win quite a lot, especially for AudioShake. And on Moses AI, we also have some margin, winning margin. Margin is a little bit small, but still like positive. So running the same audio model, it's a flow matching model, so you run the ODs over multiple iterations. So this is like latency is another like question we are kind of curious about. The others are mostly like applications. I can like skip them. But yeah, just quickly like the on the conclusion and future direction side. Yeah, so like this
Yeah,
is a unified model and multimodal prompting, and like we are trying to improve this real-time processing and like improve it for the different complex scenarios.
thanks a lot for the great presentation. So I would like to ask the audience to raise their hand or drop the question in the chat, or a couple of them. So maybe we could start with, have you tried using SAG for evaluating noise suppression outputs? How does it compare with other metrics like DNS, MOS for NISQ, etc.?
You mean for evaluation?
Yeah. So they ask about, have you tried using SAG for evaluating noise suppression output and how it compares with other metrics like DNS MOS?
Yeah, so like we compare to so first is we compare to the like baselines. We compare to different like baselines in terms of correlation. And SH is like much higher than these baselines. So in the real real like evaluation, let's say when we evaluate the same audio model, for some benchmarks where we have the ground truth, like we also compare to they use more like traditional metrics and like just to help us like pick up the model. And these metrics like for like instrument is also quite helpful. Like MCD, LSD is also like useful. So we kind of use a combination of them for like
Okay.
if you have a ground truth.
Okay. Another question is about the development path of SAM audio across different prompt modalities. Did you first build the text prompt version and then extend it to a span and visual prompting, or were these developed jointly? Also, if I want to add new prompt types, such as music mimicking prompt, like those in guide, step former or enrollment speech for target speech extraction, what would you recommend to use them?
I think in the development, we start individually first, right? We try to build like separate prototype. And then after we have like good recipe for each modality, we merge them into like one model. So, but when you merge it, you need to retrain the model basically. But I think if you want to add, because I think this current model is already like good foundational model, which is like have like strong generation capability itself. So we do like pre-training, large scale pre-training, and then we do fine tuning basically. So it's pretty robust with like any type of audio. I think if you want to do like some specialized tasks, you can just like easily add like some initiate like new projection model, or maybe fine tune one of those. Projection model, I think should be working well already.
Yeah, I think like for the audio prompt, that's also something we initially like planned, but like we didn't end up adding that in the model. So, but it should be pretty like straightforward. You add some like some branch on top of like as an input. Say use a clap audio encoder, should be like already have a higher similarity to the text prompting, and doing some like a lower depth, like just doing some like training strategy like schedule based on that. That should be already performing pretty well, fine tuning.
Okay, perfect. There's one question about target formulation. As you mentioned, in classic MSS, we usually predict mask and then apply to a spectrogram, while in generative approach, we instead generate the target signal directly. So they ask, I'm still curious about your opinion about predicting the mask using a flow matching objective. It seems this could simplify things since both the target and residual signal can be obtained from a single mask.
I think. Oh, go ahead.
Yeah, so like in the generative, like we didn't do the mask, like more like from conceptually is you know, if you directly, you kind of put a very high constraint on the target and residue. You always make sure like they add each other and you should be equal to the target. But like these can create some artifacts, as we like notice. And like real time, sometimes it's very hard to know like the exact say target sound. Say like you extract target sound, and if you have like some volume, very slight volume change in certain timestamps, you like human ear may not like notice that, but like when you extract, like when you do like subtract that from the mixture in the residual, you might hear some artifacts. Right? So that's why like just in at like very initial stage, we didn't go for the like masking, but just predict these two directly from the model.
I see.
Yeah, and
Another
then I
question.
think
Oh, sorry.
Yeah.
Yeah, then I think in addition, I think like for this kind of, like generative model itself, I think it's more natural directly if you like try to model the audio directly instead of this kind of mask where you think mask usually like is like kind of like byproduct from this specific task. Right? Because we directly model the audio during the pre-training itself, you can also like train the audio generation model first and then you fine tune it into like more specific tasks like this kind of audio separation.
I see. Another question is about how do you evaluate or validate human annotation and how you remove the incorrect annotation?
Yeah, so for the human annotation, so first is before launching, say the evaluation or like annotation for the like judge model, we always do this like pilot queue. So we measure. So we first like within our group, like us like researchers, we write annotation and we make sure like we agree. Then we like scale up and pick up like scale up to the human annotation platform, and we let a small like group randomly sample a small group of workers let them annotate. So we measure how their like quality aligns with us. So if there are some outliers, we need to like remove that from the queue. And if they are consistently lower, we will kind of considering revisiting these instructions, like making it higher correlated with us. And also another thing I want to point out is we do this like pairwise. So like our experience is if you do the pairwise, it's very effective, much more effective than if you do the absolute scale, like just let the humans see like a single example. So this is also very useful to get like reliable annotation.
I see. I have maybe one final question myself. So it seems that, for example, when you work with large audio language models, the exact prompt that you use could affect a lot on the performance. Do you have you seen the same basically sensitivity to the types of prompt that you use in your model? Like how you form your prompt or different kind of paraphrasing the same prompt. Do you see any sensitivity to that?
So I think in general, when we train this like text prompted model, we already like go through like we try to compact them into like the non-phrase and verb phrase. So basically, I think I agree. Like let's say you do like describe thing with the like natural language full sentence. I think there are many
Mhm,
variations there, but because we try to collapse them into like like smaller space like non-phrase and verb phrase, I think it's smaller variation that can happen. Basically, like if you want to do dog barking basically dog barking
mhm,
something. But I think we also like apply some of LLM. So we try to ask the LLM to create like some variations based on this concept,
mhm.
and then it can help like improve the model robustness itself. Yeah.
I see. I
Yeah,
see.
and also just a quick thing to add on there is like we do all the data augmentation to like mitigate that. So when you like use that, actually we still sometimes notice like you might have some like ambiguity like or sensitivity like use like guitar versus like guitars. Sometimes like
Mhm,
you might like have get different results. So like in practice, say you use a model, sometimes people also notice that in like put that in a guitar verse. So they notice certain like especially very high standards, you notice some like sensitivity. So I think like you might need some like prompt engineering for that, or like trying
mhm.
to doing some like re-ranking based on the different prompts, like just rephrase that at test time. That should be also helpful. Yeah.
I see. I see. Perfect. I think that we go over all the questions. Thanks, everyone. Thanks you both for the great presentation. Announcement for next week. We have Jonathan Lurks from Mitsubishi Electronic Research Laboratories talking about prompt condition unified audio modeling. Thank you, everyone, for joining and looking forward to meeting you all next week.